Okay. Today I think we'll finish the part about the models, the modeling. Yesterday we saw some that main way to describe stellar structure with the polytropes, some of the first results. At the beginning, yeah, I know it was not really exciting with all the calculation of the properties, physical properties. Then, okay, we saw the chandrasekhar mass and the Eddington luminosity. Eddington is quite famous in this stellar structure because he was the first. In fact, he discovered this Eddington luminosity. It is a luminosity that when you reach it, the stellar object started to lose gas because the pressure is too high, the relative pressure too high, so the gas is pushed away. Especially you can see this more than nearly massive stars, but in the accretion disk it's quite common that the luminosity is what causes the accretion disk to be disrupted because it started to produce too much luminosity and the pressure push away the gas. And we saw that above and high for massive stars, and the luminosity can start to be a problem. So a massive star can have some envelope losing due to the high luminosity. The next it's something again connected to Eddington. That is the standard, what is called standard model or Eddington model. That is a model that was designed by Eddington that tried to simplify. We define the ratio among luminosity and the mass at a certain radius as a function eta multiplied by the ratio among the total luminosity and the total mass, or luminosity at the surface and the mass on the surface. That means that this eta can be seen as the mean energy production rate at a certain radius divided this mean calculating on all the mass of the stars. And we saw that, for example, for the sun, this is above the total mean energy production rate is 2 erg per grams per second. And this, okay, depends on the radius. For this reason, we can assume that eta on the surface is 1, y on the center is just the epsilon, the production rate for the nuclear reaction, divided the mean, and this is obviously bigger than 1. We saw this epsilon more or less is 20 for the sun. So, for example, for the sun, in the center, eta the value is like 10. And obviously, the derivative or the behavior of the eta with the radius is the decrease from the center to outside. It goes, for example, for the sun from more or less 10 to 1 on the surface. If we rewrite then the derivative among relative pressure and the total pressure, we have this value we saw yesterday that is connected with the luminosity. But introducing eta, we can substitute the luminosity at a certain radius and the mass at a certain radius, this ratio with L divided M, that is a constant multiplied by eta, and so we got this. It is a constant multiplied kappa by eta. Kappa is the opacity. This term identify the opacity, and eta is what we saw previously. We know that the opacity decreases with the radius. There is a radial derivative is no increase with the radius. So it's greater than 0. This is because in the center usually we have just electron scatter. That is really a small value, while in the outer envelope, outer layers, we usually have bound-free capacity, and this can be really high. We saw previously the equation that the exponent you have 10 to an exponent quite big. This is because obviously it's really easier than light can interact with the atom, with the electron bounded in the orbit of just a random electron in the plasma. The standard model do an assumption to simplify everything that since the eta decrease with the radius and the opacity increase with the radius, we can estimate that the product can be quite constant. And this is the famous we saw at the beginning. We can use it to simplify to have a simple model. We determine that the property is uniform, and in this case is this product. We recall this product kappa r because it's essentially the opacity on the surface, because we saw that on the surface eta is 1. So this means that this derivative is a constant, because we have here the constant, clearly, we have our constant value. In this term, we suppose it is constant inside the star. So if it is constant, means that the ratio among the two variable is a constant, that constant, or that pressure ratio is equal to the constant multiplied by the total pressure. This ratio is 1 minus beta, as we defined earlier. The beta is the ratio among the gas pressure and the total pressure. But this is also the ratio among luminosity and electron luminosity. Previously, we calculated that for stars in general, we can put together that P is equal this value multiply density to the 4/3. And we know for polytrops that the mass is defined as in this way, with a constant that depends on the index of the solution, numerical, exactly. Then the function of the constant here of the equation state. So putting all together, because we can have this equation that is called Eddington quadratic equation that give us a relation among the beta that give us the value for ratio between pressure and gas and the total mass. This constant of the term constant. This term is defined by the solution that we choose polytope of index 3, and the mass to the square and the molecular mass to the 4th. So at the end, we can write this equation this way, showing that the the relation among how the pressure is divided among gas and radiation, and the mass and the chemistry, essentially. Essentially, we see that B is mainly or equal to 0 from looking at the graph of this one. That means that this value is 6.3 or approximately 1, that it means that it's essentially the gas, from the same value, the same variable, the mass multiplied by molecular mass to the square less than 1.5. More or less mean that more or less 0, among 0, between 0 and 0.2, and more or less 1 from between 1 and 0.8. And we see that essentially the value is quite mainly or just gas easily or radiative. That means that just for a small range of mass, you have that the gas and the radiative are comparable among them. Usually it's mainly the gas that gives the pressure, or mainly the radiation. Something that this model or this equation can tell us is that if you fix the mu, the molar mass, so essentially the chemistry, the beta decrease with the mass. So increasing the mass, we have the pressure, radiative pressure are bigger than gas pressure. We saw something also yesterday. Then, if you calculate the luminosity that here we can see what depends on the opacity, opposition, the ratio among how the gas pressure is important, and the mass. Keeping more or less constant the other, we see that supposing that the opacity more or less the same among the stars, the composition is the same, and there is not a big change in beta, the luminosity is more or less proportional to the square, to the cube of the mass, something that we saw also earlier. Other things that inside the stars, we can assume that stars, the mass is fixed and the composition more or less is fixed. So we can suppose that the beta is more or less constant inside the star. It is something we just supposed and not used, not really understood. Here we show that it's actually true. Inside the stars, the beta doesn't change a lot. Not exactly, actually. There are some change inside, but not so strong. At least we can, for a simple model, we can suppose that it is quite constant. It makes sense. And for certain stars, so we fixed M, and just here to remember that you can do a calculation, see the luminosity of the sun, how much is in in mass, calculate for all the 10 to the 10 here, that some more or less will survive, and you can see that it's less than 0.1%, or at least less than 1% is the mass is transformed in luminosity. So you can assume definitely that for a star, mean in its life, the mass is constant. Then we see there are actually in the evolution, maybe Reggian branch and the Central branch, there is quite a loss, an important loss of mass due to the wind, but this is also something that is less than 10% of the life of the star. So if you fix M, we know that the molecular mass decomposition vary with the time, and the moon increase with time. We can see here the inverse decrease because it's moving here, and this is quite big. So if at the beginning was like 0.8, because this is 7.7, this is 28 divided by 4.7, actually 0.77. Then if you deplete this one and this one, start to deplete this one in here, this the mean atomic mass number is quite big, so can be definitely negligible. So this decrease, but since the inverse will increase. Knowing this, we can see that then the beta, the ratio, decrease with time. That means that the pressure, the radiative pressure start to be with the time more important than the gas pressure. That being suggested that during the life of the stars, the luminosity can approach the luminosity, evident luminosity, and can be a mass loss that actually we saw in I mentioned before. There is in latest phases of the stage of the life of the stars, meaning when this red giant, supergiant, red supergiant, red giant, there is the luminosity increase, and we have strong mass loss also because the envelope starts to have a strong opacity since it's falling down, and this means that opacity is start to be really, really important. Oops, this one. As I mentioned, we now saw several of the interesting models that can be to understand it. One other interesting model is the model with the uniform energy source. That means that usually nuclear reaction is just in the core, so quite concentrated. In this case, we suppose the energy source is distributed, is uniform in all the stars. That means that cannot be nuclear reaction. But a classical example is a star in gravitational contraction. When a star is forming, you have energy loss due to the contraction, but this energy loss is uniform inside of the stars, not that just one part is losing energy by contraction and the other not. It's uniform. So we can suppose this one, and supposing the radiative transfer value inside the whole star. This to simplify. Otherwise, you have to consider the convection transport and the limit to the gradient and so on. So the epsilon interradius is a constant and is equal to the gravitational energy production rate. This means also that L over n is a certain radius is equal to the mass of side, and be equal to epsilon, because it's uniform. So up to the central radius, the energy you are produce increase with the mass. So this term, let's say, is constant, and also it's a constant deceleration inside all the star. We calculate this gradient that, and we suppose that it's due to radiative transfer. We suppose that the radiative transfer is the one that is working inside the star. So the gradient is the one due to the radiation. We got this equation. We do some change, supposing a certain opacity with the Kramer law, depending only on density and temperature, substituting the density here with the equation of state, because we suppose that is supported by gas. So pressure, but the gas, simplify in this way. Okay, it's a lot of calculation with this formula that depend on the several coefficients. To simplify, we suppose that at the core, the gradient, this gradient we saw here is equal to this value. That brings us a polytrope. It's a way to simplify the things to have something more easy to manage. We got the index, polytropic index Ni, that is equal to this value. That should be also a relation for this one with the adiabatic coefficient. Using the mass radius Kn relation, we do the calculation. We have this relation among the luminosity, molecular mass, total mass, and radius of the stars. As usual, we are interested to see this kind of relation. Here, I just put something that was quite usual, the constant you can find always when you find a luminosity, say opacity below. Here, I didn't put for you all the detail, but it's an awful equation depending on the exponent for the opacity, the polytropic index, and the solution for the surface. What's important are just putting inside you see Kramer opacity with the classical value of 1 at 3.5 that give us a polytropic index of 3.25. It is a little different from the classical we saw before, and give us this relation among luminosity and the three variables, the three properties. You see the change with the radius is not so strong. If you just consider a constant opacity, just electroscatter, we have a classical polytropic index 3 as usual, and with the classical relation between luminosity depending on the cube of the mass. Why doing all the calculation? This is because we saw that for this kind of model, that's essentially a star that is contracting and depend barely, slightly from the radius, or not at all. This gradient is just minus 0.5, and the other for constant opacity you have just that doesn't depend on the radius. That give us during contraction, the luminosity can be more or less constant, and this is actually we observe. Lucky. Okay, update it to the register of the present. So we with this model, in uniform source energy, we can see that at the end we can suppose the luminosity is quite constant for a star that is contracting and just energy by the contraction. And this is something we observe in protostellar when are moving, you will see in the Eston-Russell diagram, the stars are more or less forming what is called the Hayashi region, Hayashi line. It is a more or less a vertical line. We see later the characteristic of this area, and move toward the main sequence in more or less in horizontal direction. That means that during the contraction, the stars maintain the luminosity up to the main sequence. It is just for contraction. Also, it's clear that, as we saw, that is also the Kelvin-Helmholtz time scale, and this also explains why the big stars is so quick, also because they have really high luminosity during this mass. Other interesting case is into thermal model, when the temperature is constant, the gradient of the temperature is 0, you have no gradient inside the stars. That also should mean that you have no flux of radiation, because you have no radiation, you have no gradient temperature, as we saw previously. But so if you do some calculation, we see that when both pressure of gas and pressure of radiation, because of the pressure that is, because it depends on the temperature, not on the gradient of the temperature. At the end, the pressure, total pressure is just a constant multiplying the density plus another constant. Doing something similar with the polytrope, just we put that the density is equal to the central density multiplied not by the function to the end, but it's exponential to the minus c. Radius defined in similar way. We have this constant multiplied by this dimensional variable, and we got a similar to the Lane-Emden equation, but with the exponential. For epsilon 0 to the center, the phi is 0 by definition, because you have the central density. It also boundary condition that the phi is derivative of the center must be 0. As we saw, you cannot have cuspid inside. You cannot have that the change in the density have abruptly change in the gradient passing through the center. Must be continuous. Otherwise, if you have abruptive change, you will have some movement or force, so on. Doing the calculation, we have this result, the mass and the mean density is equal. Mainly, we saw that the mass go to the square in of the distance. that means that these things increase continuously. This equation has no analytic solution. You have to just crunch it with the computer, with a calculation, approximation. Usually you create a tailored expansion of the T, and you put inside and see what came outside. And one solution is that we don't have a C1, and we don't have a surface. The density is never equal to 0. No surface, so like the political within 5 or more. That means that a star cannot be fully isothermal. But part of the star, yes, we will see, essentially, I mentioned, that the degenerate gas of electrons, since the movement of electrons is given not by the temperature, but the statistic, time Dirac, so the P, the momentum, is really high, the conductive transfer is really good, and it's permit usually the generate gas inside the core to be quite isothermal. That means we can have this kind of solution, but just for one part of the star, usually the inner part. And this actually is good for every compact object where there is a degenerate state. White dwarf, also neutron stars, and so on. Other model that we can calculate is the point source model, is where we suppose that the epsilon, depending on with the r, it's just constant for in a small area, small part of internal. To be extreme, just 1 point, I say the name, but actually can be also a little bigger, but the important is really big, smaller than the radius, and outside is just 0. That is essentially how work a star, more or less, because usually its the production of energy is just inside in the core of the star, that is 1 part. For the sun, as we saw, we calculate is inside the 30% of the radius. Anyway, supposing homogeneous composition, this can be also helpful, the model, to calculate the outer layer of the envelope of the stars, where there is no energy production, considering that the energy is all produced in the center, because it doesn't change a lot in the solution. So, because of this, we can see that for the luminosity, for the radius bigger than this delta, is just constant, the total luminosity. Supposing the opacity in this way, it is all the classical solution. You have the hydrostatic equation, radiative relation, in this case with the pressure, but you can rewrite. And continuity, putting inside, you imagine a little, doing here a second derivative, so you take away this one, and you got this equation that can be assumed in this way, with the second derivative from gas, pressure of the gas and pressure of radiation, it's equal to this constant multiplied by the radius to the 4th power. Note that is strongly is just to show you how is on an example. And here we using the equation state, doing some modification, and getting this relation among the inverse of the radius and the pressure radiation that depend in this way. Then if you using a dimensional variable for relative pressure, gas pressure, and inverse of the radius, you have just this just simple equation that is are easiest to manage. You can calculate the relation of the gas pressure, radiative pressure, temperature, and density with the radius. You can inverse the relation, and you get that relation among luminosity and the mass. And we see that this exponent is not exactly constant for all the mass, but is steeper for low mass than the large mass. That means that the luminosity increase more at the lower mass than on the higher mass, a large mass. Large mass, the increase is lower. That is, in fact, something we observe. Usually, for lower mass, the second around 5, and for large, it's like 3. That result is not something constant. Another something that is used quite a lot is the homology relation in modeling. This is a way to essentially to simplify the work, to make it quicker. Stellar structures relying on identical physical assumption or condition. You have different stars, and you have but the equation here are the same. So you suppose that changing mass, radius, something like that, you should have the structure that are similar properties. So one solution can be transformed in another by similarity. The homology is a geometrical transformation. It's not that transform one object in a similar to maintain exactly all the proportion, but maintain some ratio. An example is that if you suppose that phi n is a solution of the Lane-Anden equation, we can see that theta n, that is a constant multiplied to the 2 divided n minus 1, multiplied for the phi, where we instead of using c directly, we use as variable c, the constant multiplied with xc, is another solution. If you put this equation inside the Lane-Anden equation, at the end, you'll get again the classical elimination without the constant, because it's taken away from the equation. So this means that if we can find a solution, just multiplying with the constant in this way, we can have other solution continuous. Except for the polynomial index 1, because it goes away. That is the sin of xc divided xc. Quite clear solution. So also given two stars of each one with his mass and with his radius, we can say they are homologous if the ratio for among the mass and certain radius with the total mass is this ratio is equal to the ratio corresponding to mass and the certain radius of this radius total mass This when with R and R prime they are homologous point. This means that they are follow the rule that the ratio of the radius respect to the total radius of the stars are equal. So, for example, in half of the radius for those stars, inside there is half, can be half on the mass or 1/3, but is this ratio to be constant. Increasing the for one stars, the position, the shape essentially of the how depend the mass, the ratio of the mass on certain radius divided total mass that vary respect to the radius, respect to the total radius, relative radius. For the two stars, the two shapes are equivalent. Or, saying another way, spherical shell of homologous mass stayed at homologous radius. That means, let's say that we form the stars with bigger or smaller, but the distribution stay more or less the same. This permits us to study the two systems quite similar. Supposing they are similarly, we define this adimensional variable, the ratio between the relative mass inside the star, a certain radius, and the ratio of the radius considered in function of this radius of the mass. We call this theta. We can do it for all, for density, the energy production rate, and the luminosity. And we have so that given one system, one star that is a solution, we can put there to have a solution for the other stars, but this gives us essentially a stellar equation gives us a new set of equations with a new variable, because we started with the stellar structure equation. We insert the changing the for example, instead of density we put delta prime multiplied by V, and instead of epsilon prime multiplied by E, instead of the luminosity L prime multiplied by small l, we put together, then the equation can be separated. We have the classical part and multiplied by a part that is just a function of this new dimensional variable. And so this should be 1. And what gives us, we have a new set of equations among this dimensional value, depending on the several exponents we choose for opacity, the equation of state, because it keeps it quite general. Some interesting can be if the density doesn't depend on the temperature, like the classical degenerate state. We have the radius just depend on the mass to a certain exponent. This exponent is a function of the previous value. And for classical degenerate matter, not relativistic, we have that the radius depend on the inverse of the third root of the mass, something that we saw previous. For an ideal gas with a constant opacity, putting together, we have this relation with this exponent that is a little less than 1, doesn't change a lot. And from this one, we can do the calculation, transporting not more in luminosity with the mass, but luminosity with the temperature of the surface, effective temperature. We have just that we see the logarithm of the luminosity, that, as you remember, logarithm of luminosity is in the magnitude, is proportional to the logarithm of the temperature, effective temperature, plus a constant, that is exactly the actual diagram. So this homology relation can also give us some result like that there is a meaning in the HR diagram given by the stellar structure equation. That means that all the stars stay in a certain position. Then, obviously, as we saw, it's not so easy that the polytrope can describe perfectly stars. We check it for several models. We check for several characteristics. For example, we can have isothermal one, or the a certain polytrope. For if there's a radiative, we have one point source, we have a solution. We can have a degenerate state of the matter, have another polytropes, or relativistic degenerate matter and another polytrope. The radiative part has one polytrope. The convective part, since is the internal part, it's the gradient is strongly fixed on the diabatic. The diabatic one so goes with his polytropic index due to the adiabatic coefficient. We saw that are connected, the two, between, because also the adiabatic transformation have a relation between pressure and density in the type of polytrope. So we have started actually the polytrope index is not constant, easily can change. So as we saw at the beginning, usually we don't solve a solution for all the stars. We can need to separate several parts of the stars, apply the model, and then to try to connect. This is essentially what is done. You combine the polytropes. You are not just a star with just one. You create one polytrope for each part. Then you need to connect all this solution. In the matching point, is important that you have a continuous for the pressure, the temperature, the mass, and the radius. Obviously, the mass, because you cannot have that essentially in up to the certain radius. You have half of the mass, a little more after you have total more mass. You can have infinite density there, or have negative density. Mass cannot decrease. The radius makes sense. You cannot have a wormhole inside the stars. You have to pass continuously, but must be essentially derivable, since you have to be continuous, and the derivative must be continuous. Because if the derivative is not continuous, also there you can have some strong variation and cause problem. Usually, just in case there is a correction in between to smooth the derivative, is not perfectly continuous. To create all these things, usually is what to homology variable we saw before. homology is really used for this kind. Use these two variables defined this way. In this way, they are equal to center value. Then you find a solution in the intersection of this plane. Here you will show just spotlight. For the Kipton temporal assumption in the UV space to connect several type using radioactive envelope with different type of core, the convective core, on isothermal core with different type of envelope. Usually isothermal core, this means that degenerate mass, so we have a red giant stars. That means also the envelope should be convex. In radioactive core envelope, usually it's more common in the high mass star. The sun is in the between, of quite the envelope is quite radiative, and the core in massive stars are convective. In fact, convective core, as you say, the radiative envelope. It's maybe once I think that is definitely they are drawing this graph and looking for intersection. Now, okay, you have a program that can find them, but you can see that sometimes the solution have complicated shape, so it's not so easy to match the solution between them. Oh, I decided to stop here because it's also this part was quite strong. This also the case some calculation will be see the collapsing of the polytrope. You can, it's another case where essentially are a lot of calculation. You can see here from the collapsing polytropes. It's just a really nice exercise of calculus. I don't want to what nice things that if you, I think you already see the quantic, and as in quantic, the solution you take separate the two parts, one depending on the time and one depending on the space, and so at the end you got here here you can see this all the calculation to get this one. It is a part that is depending on the temporal part of the collapse on the other. This calculation is done just for polytrope 3 because it's the one where the temporal part for the deviation from the equilibrium is like more important, and gives a solution that is essentially, since there are two parts, like in quantic, you separate saying that they are proportional to a certain constant. In the Schrödinger equation, if I remember, of the time, also the other was the energy. The type was energy. This I remember for the time what was, but you have also here you see you do the calculation, you obtain something similar to them then an equation, but just with a lambda that is the variation from the equilibrium, and we give the characteristic for the collapse and the solution. But doesn't make sense to show more. It's it's a nice, if you want to see a little more something detail in the Kipnan, there is also a full chapter about homology relation. But okay, this course is not about modeling stars. It's just to show how is it working, studying the structure. And for the reason I decided to show several model interesting cases that can be, not going too much in detail in general. So at the end, we saw the stellar structure as defined by these equations. Hydrostatic equilibrium principally because the stars have to be in equilibrium. The continuity, radiative transfer, thermal equilibrium, equation state, and other sub equation due to the to define the singular variable. Here for the define the composition. We have some boundary condition that something of obvious, the mass and the velocity of the center must be 0. Then we have central density, central temperature, central pressure. Mainly at the surface, the mass must be the total mass, the luminosity we observe. And for density, temperature, and pressure can be the actual value or just 0, depending how we want to simplify the system. The Vogt-Ressler theorem tells us that we fix the mass and the distribution chemical elements. We have a good distribution of all the stars. In fact, we saw several times mass and molecular mass it's entering the equation, determining several physical properties. And now also we saw something, the matching method, that is important because we cannot have a solution for all the stars. Sometimes you have to consider several parts. And for the correlation, we have the polytrope that gives up several characteristics. Depending, using polytrope of this simple equation, independent of the physical properties. We can just calculate this one, obtain. We saw that from this equation we can obtain other additional equation with just a constant. We saw that we are most interested usually in solution with index among 1 and 5 excluded, and principally n 3 alpha and 3. 3 alpha, this is the non-relativistic generated gas, while polytrope index 3 is the relativistic generated gas and normal stars in mixed sequence. Radiative stars. We got several descriptions of several, some nice result we obtained. But here already that is a mass radius relation for the polytrope. So for a star should be a relation between the mass and the radius. Essentially, in this case, talking about the main sequence, because if you move outside, also consider it a giant, but they are in different evolution states. So The internal situation is different. They are not comparable. We found using political that there is a Chandrasekhar mass, that is a mass limit for relativistic degenerate core or object. It's not possible to have mass above a certain value. We saw that there is a limit, also studying with this one, is a limit for the luminosity above which the pressure, radiation pressure is too strong and will lead the stars to go in not more in the static equilibrium, and so using more in the envelope will start to lose some part of the standard envelope. Then we studied we see several examples of the standard model with the quadratic Eddington quadratic equation. They give us a relation among the relation and how the gas pressure and the radiative pressure are important inside the star and depend on the mass and its composition. And other models, they are interesting just to show some characteristics that we see later. It's here not the calculation that are important, it's just the result. Some models that are quite important because are the uniform energy source is a star in computational contraction. Isothermal model is classical degenerate core. Consort model is more in general stars, the envelope of the stars in radiative. In homogeneous composition, the composition is quite simple. It is homogeneous because usually since there is no source of energy, there is no nuclear reaction, the composition cannot change, stay there. The convection that there could be doesn't change a lot because you are just mixing something that is the same. If you have water that's boiling, its composition doesn't change, just because boiling, because it's moving. Obviously, if you put inside some salt, the convection will mix the water and make it salty everywhere. But in this case, if not, or if you have a core for convection, it's the same because it's the core in this case very easily considered small respect to the other. So another point is we just the point source model consider outside the area is producing energy. Considering it is like in a point, a typical modern physical model. And okay, just a mention about the homology relation and combining polytropes to understand a little better how you are modeling a star. It's not just you have this result and you calculate all the solution one by one. You can create one solution and try to see how to propagate to different cases this solution. With the homology, or using in this case this homology variables to combine solution to see where they match, and in this way combine several shells for each part of the stars one solution, and we need to combine each other. Tomorrow we'll start to see more of the stability. It will applying of the model to see when a star is stable and when it is not stable. You have some question? I don't know, because of this part of today was mainly descriptive. It's not that.
No, not by me.
If you want more detail, the Kittenpenam is giving a lot. In fact, it's a nice text, but definitely it's can be also really heavy to follow, because I'm giving you all the detail, all the calculation, and all small. It's but at least give everything, and not
Okay,
passing over. But yeah, homology
I'll figure
relation,
out.
something that can be important to know that they exist. If maybe you later do some modeling, the course should be for everyone. So if you're interested in astronomy, we don't have a modeling. But in physics, there are some modeling. I don't know if they're using this kind. At least you see some example of physical modeling of this kind, how it's working. Okay, if there is no
Okay,
question,
bye.
we can close here.
See you
Bye.
tomorrow.
See you.
Bye.
Pause. Stop share.